Okay, welcome back to section 3. In this video we're going to finish talking about section 3. We're going to specifically continue talking about graphing logarithmic functions, and then we're going to talk a little bit about how we can use a word problem to write the inverse of an exponential function. Just a reminder, this is the parent function log base b of x. In this graph, b is greater than 1. The base of my logarithm is greater than 1. Remember, these are the 3 points that show up on that graph. And the b is based on the base of the logarithm. So I have the point b1, 1, 0, and 1 over b, negative 1. When b is between 0 and 1, so like we see over here on this other graph, this is the inverse of exponential decay. The same 3 points are still there, but it looks a little bit different because it's the reflection over y equals x of an exponential decay graph. But I still have the point b1, 1 over 0, 1, 0, and 1 over b, negative 1. So take a look at this first graph that we have here. We're going to graph the function f of x equals log base 3 of x. The points that we're going to be able to graph are based on that base. So we identify the base, which is 3, right? That's step 1. Then we find those 3 points on the graph. Since 3 is greater than 1, we're looking at the first graph, the graph on the left-hand side. So we have 1 over b, negative 1, 1, 0, and b1. So our points are going to be 1/3, negative 1, 1, 0, and 3, 1. Those are going to be the points that we graph. Why do those work? Because if I plug in 3 to my logarithm, if I say, okay, what's log base 3 of 3, if we're looking at this point, right? Why does that point work? Log base 3 of 3 equals what? Well, we're saying 3 to what power equals 3? 3 to the first equals 3. So log base 3 of 3 is 1. That's why that point works. Why does 1, 0 work? Because if I plug in 1 for x, I get log base 3 of 1 equals what? Remember, this what is an exponent. So 3 to what power equals 1? 3 to the 0 equals 1. So when I plug in 1, I get 0. Then we're just going to sketch our graph. And it looks like this. So if you notice, we have the point 1/3, negative 1. That's right here. We have the point 1, 0, and we have the point 3, 1. And then we use our knowledge of the logarithmic function. We know that the y-axis is an asymptote, so it gets infinitely close there. And then it continues to grow to the right at the same rate. Okay, now we're going to do one where the base of our logarithm is between 0 and 1. So our base here is 1/4. Just like the last one, we have these points, 1/4, 1, that's b1, then 1, 0, and then 1 over b, negative 1, right? This is 1 over 1/4. 1 divided by 1/4 is 4. That's where they got that 4. And then we sketch our graph. So you can see here I have the point 1, 0, I have the point 4, negative 1, and I have the point 1/4, 1. And our graph looks like this. We know that the base of our logarithm was between 0 and 1. So again, the y-axis is our asymptote, but this time I'm coming from positive infinity and coming down, and it will continue to decrease as x goes to positive infinity. All right, I want you guys to try this one. All right, you should have gotten D when you graph this. Your 3 points should be 1/5, negative 1, which we can see here, 1, 0, and 5, 1. And again, we know that the y-axis is an asymptote, so this is the graph that most closely matches with those 3 points. All right, try this one where the base is between 0 and 1. In this case, you should have answered A, and your points that you should have are these 3 points right here. So we can see that A most closely matches that. All right, just like with any function, that was our parent function, we can talk about transformations of logarithmic functions. It's exactly the same as it has always been. The h inside of the logarithm is a horizontal translation. So it's x minus h. So if it's x minus 3, it moves to the right 3. If it's x minus negative 2 or x plus 2, it moves to the left 2. So that hasn't changed. K, adding and subtracting a number outside of my function, is still a vertical translation. Moves it up or down that many units. And then A, the coefficient of the logarithm, gives me orientation and shape. So remember, if A is negative, I get a reflection across the x-axis. If the absolute value of A, so ignoring the negative, is greater than 1, then I get a vertical stretch. If it's between 0 and 1, I get a vertical compression, so it shrinks it vertically. Those rules are always the same for all functions. So let's take a look at this function. 1/3 times log base 6 of x minus 1. Notice that this negative 1 is like my k. It's outside of the logarithm. It's not inside because there's no parentheses. So that's going to move it down 1 unit. And the 1/3 in front is going to be a vertical compression. So it's going to shrink it down by 1/3. Which we have here. There's no horizontal shift because there's nothing added or subtracted to the x inside of the function. So when I make my graph, it looks like this. It shifted down 1 unit. So notice normally it would go through the point 1, 0, but that's been shifted down. And then it's been vertically compressed by 1/3. So let's compare a little bit what's happening. These 3 points would be my original points I would have graphed with the function log base 6 of x. When I plug in 6, I get 1. When I plug in 1, I get 0. When I plug in 1, 6, I get negative 1. So let's see what happens when we transform them. When I plug in 6, right, to this function, I have 1/3 times log base 6 of 6 minus 1, right? We know log base 6 of 6 is 1, because that's our original point. That's what happens when I take the log of itself, the same as the base. So I have 1/3 times 1 minus 1. 1/3 times 1 is 1/3. 1/3 minus 1 is negative 2/3. Same thing, when I plug in 1, I would usually get 0, right? So 1/3 times log base 6 of 1 minus 1. Log base 6 of 1 is 0. So 0 minus 1 is negative 1. So you can kind of see how the transformation is working. It's taking the y coordinate and it's multiplying it by 1/3, so it's compressing it and making it smaller, and then subtracting 1. Okay, take a look at this one. 4 times log base 1/3 of the quantity x plus 2. So this would be our original function, our parent function. The absolute value of A is 4, so I'm getting a vertical stretch. My y values will be stretched by 4. H is negative 2 because this is like x minus negative 2, so it's going to be moved 2 units to the left. And k equals 0. There's nothing added or subtracted out here, so there's no vertical shift. And there's no negative in front, so there's no reflection over the x-axis. So this is what my graph looks like. So this is what the graph looks like. Again, remember, originally would have gone through 1, 0. You can see that that has been moved to the left 2 and then stretched 4. So what happens normally when I plug in 1, sorry, I think I said that a little bit weird, so I'm going to say it again. Normally I would have the point 1, 0, right? Well, what happens when I plug in 1 to this function with the transformation, I get the 4 times log base 1/3 of 1 plus 2, so that's 4 times log base 1/3 of 3. Log base 1/3 of 3 is negative 1. Negative 1 times 4 is negative 4. So that point moved down to here. Okay? Another point. All right, I want you guys to try graphing this function with its transformations. Okay, in this case you should have gotten B. Notice here that this is a transformation down 3 and a vertical compression of 1/4. All right, let's take a look at this one, see if you can identify the transformations. Okay, for this one you should have gotten D. This is moved to the right 1. We know that the base is between 0 and 1, and so we know it's going to be the reflection of an exponential decay. So that takes A out of the running. And then this 2 is a vertical stretch of 2. Okay, let's take a look at these word problems to end this section. It says, at Earth's surface, the air pressure is defined as 1 atmosphere. Pressure decreases by about 20% for each mile of altitude. Atmospheric pressure can be modeled by this exponential equation. This is an exponential equation because my independent variable is in the exponent, where x measures the altitude in miles. Find the atmospheric pressure in atmospheres at an altitude of 8 miles. Okay, so this is pretty easy. Here's our original equation. I know that x is the altitude in miles. If I'm given an altitude of 8 miles, I just plug in 8. And I use a calculator for this, and I get about 0.168 atmosphere. Okay, because atmosphere here is my unit, and we do not answer word problems without units. All right, part B, we have the same information, the 20% decrease for each mile of altitude. I have the same model. It says write an equation for the inverse of the function. So to do the inverse, remember we switch x and y. In this case, it's x and p. X is my independent variable. P is my dependent variable, like y. So I switch those, and now I want to solve for p. Well, p is in the exponent. So how can I write this as p equals? Well, remember that logarithms are a way to write things so that the exponent is equal to something. So I rewrite this in logarithmic form using the definition of a logarithm. This is x equals b to the y, and this is y equals log base b of x. So we're going back to what we did yesterday in yesterday's video, and using the definition of a logarithm. So this would now be my inverse function. P equals the pressure equals log base 0.8 of x. All right, you guys try this one. Okay, you should have gotten B, which is 41 pounds per square inch. This is how you should have set it up. The reason I have a 7 here is because notice that x is the number of 50-mile trips. So if we drive 350 miles, I drove 7 sets of 50 miles. That's why the 7 is there. Then you use a calculator to do that calculation, and you should get about 41 pounds per square inch. Okay, take a look at this one. All right, your inverse here should be d. We start out with this function. And there is the work that you can do to get your inverse function. First, we divide by the 44 to get the exponential part by itself, and then I rewrite this exponential expression in logarithmic form. Okay, that's the end of this section. I will see you in class 2. Keep practicing. If you're still confused about the definition of logarithms and all of that, make sure that you go back and watch the first video or come get help, read the section, something to make sure that you understand it, because that is what the rest of the chapter is based on. So I'll see you later.